Good morning, everyone. My name is Niktha Sarkar, and I am the CFD Application Engineer here at KETIV Technologies. Welcome, all of you, to our ANSYS Virtual Academy session today. We have with us a very special guest, Mr. Markus Kopp, who will be presenting an overview of ANSYS tool capabilities in antenna and antenna system design. Markus is a global technical manager at ANSYS, and he has over 21 years of experience in supporting the ANSYS Electromagnetic Suite, which includes tools such as HFSS and Maxwell. We are very happy to have you here with us, Markus. Thank you so much. With that said, I'll pass it over to you, Markus. You can take it away.
Thank you so much. Thank you for that introduction. And thank you everyone for taking the time to come and attend this seminar. As Sneekta mentioned, my name is Markus Kopp. I'm a principal engineer at ANSYS, and I am the global technical manager for EBU enablement. And today we're going to discuss the types of solutions that ANSYS can provide to engineers working in the field of antenna design, and how to use our tools to help you further your designs. Now, when we speak about our tools, we actually have quite a variety and wealth of tools available, and also of different types of applications where our tools can become useful, or where our tools are useful. Now, in today's presentation, I will only be covering sections 1 and 2. But if you are interested in some of the other sections, such as the RF co-site modeling, or how to do RCS, radar signature type simulations, or radar, automotive radar, or possibly phased arrays and beamforming, do let us know, and we can have another session where we will discuss additional topics. So for today, however, we're going to focus on the different tools that ANSYS provides to the field of antenna design, and then how we help engineers determine how well their antennas work. So when we talk about electromagnetics and ANSYS, the first thing that we have to, of course, realize is that we are a physics-based simulation. In other words, everything that we do relies 100% on the rules of physics, the laws of physics. And it doesn't matter whether we're doing antenna design or signal integrity design, antenna array, antenna placement, if we're doing co-site, lightning strike, or even some very large-scale platform interactions. All of these simulations are based on tools and numerical methods that take into account the full extent of the physics that rule the behavior. And as you can see, with our simulation, or electromagnetic simulation capability, we can pretty much address any type of needs, any kind of design needs that are desired by engineers. Of course, today's topic, we're going to specifically talk about antennas. And there, you know, the challenge with antennas, speaking as an antenna engineer previous to my life at ANSYS, I used to work as an antenna engineer, and the one thing that I realized very early on in my antenna career is that designing an antenna, while challenging, is quite doable. And it's really getting the antenna to work in the location or on the platform where you would like it to work that is the challenge, right? So the real challenge is installed antenna performance. The reason for this is obviously because they are often designed in isolation. Mounting antennas oftentimes has to be done in an ad hoc manner, where they just place them where it's convenient. And of course, these types of things will impact the RF performance of your antenna and the antenna system. So it is always beneficial to know how your antenna is going to work before you build it and deploy it, by creating a virtual duplicate of the antenna and its environment. And that is really what we're going to talk about today. So when we talk about simulating antennas, historically, and for most people still today, they understand that HFSS and ANSYS provide solutions to structures that are limited in size, or actually quite small. So for instance, there is an antenna array here on the left, but it's just a simple array. It's not large or anything like that. And what people don't realize about the ANSYS solution set is that we actually have additional computational engines besides just HFSS that allow us to expand on the scale of the simulation that we're trying to do. So while we can use HFSS to do a simple antenna array as shown in the lower left, we can also use HFSS to do installed antenna performance by capitalizing on our built-in integral equation or method of moments solver. So we have a finite element solver for things that are reasonably small in size that is quite fast and extremely accurate. It's the most accurate tool in the world. And then we have a second solver that allows us to take these antennas and mount them on larger platforms such as aircraft or cars and see what their performance is going to be. And then we have our latest tool, which is what we call our shooting and bouncing array tool, which allows us to model antennas that are installed in extremely large platforms, entire battle cruisers, aircraft carriers, state-of-the-art aircraft, basically structures that are extremely huge in relationship, not just to the antenna, but also that are huge in terms of frequencies, right? So we could take X-band antennas and mount them on a battleship, and we could tell you what the performance of that antenna is going to be. So this allows us to simulate extremely large structures with antennas and calculate the antenna parameters, far field patterns, behavior of that antenna on that structure. However, to make this all work, what we have really is an interoperability between all of these different solvers. And this is what allows us to create simulations based on HFSS, where we then either involve the IE solver or the shooting bouncing array solver. And we'll see an example of that a little bit later. So HFSS as a tool provides us electromagnetic insight into really any type of structure that uses electric fields or current, voltages, etc. So it doesn't matter whether we use HFSS for antenna and wireless applications, for microwave components, RF microwave circuitry, integrated circuits or packages, right, or cross sections, or even high-speed interconnect, right? The same tool, HFSS, is used for all of these applications. And that makes it an excellent tool for any organization that deals in multiple different types of design challenges. Oops. Here we go. Now, the thing that makes HFSS such an amazing tool, and one that engineers can rely on for robust and accurate answers, is what we call automatic meshing. And what you can see here is we are designing a 4-patch antenna array, so a 2x2, and you can see the fields on the bottom, and you can see that we're going to generate a circularly polarized antenna array. But on the top, what we're looking at is we're really seeing the meshing that is done to allow us to state that HFSS has unparalleled accuracy. And the reason why we can do that, and the reason why we can say that HFSS is the most accurate tool on the market, is because it is automatic meshing. And if we look at it carefully, we can see that the mesh is changing as part of the solution process. And on the right hand side, you can see all those red squiggly lines, and what those lines represent is the return loss of this antenna. And the reason why it changes is because in simulation, whether it's electromagnetic or otherwise, what we're solving is the mesh. Depending how the mesh is constructed, we're going to get one set of results. Now, those results may or may not be accurate because the mesh is constructed poorly. What HFSS does, in order to make sure that we don't have this potential cause of error, is HFSS during the solution process automatically creates and modifies the mesh so that in the end it has a mesh that is not only structurally conformal, in other words, it captures all of the structural detail of my antenna, but is also electromagnetically appropriate to capture all of the electromagnetic effects that a particular antenna might have when it interacts with itself or the platform that it's mounted on. This is the challenge that we all face, and HFSS, due to its nature of having an automatic adaptive meshing, solves this challenge and gives us what we consider to be the most accurate and robust answer possible. If you want to have more information on how our automatic adaptive meshing works, feel free to contact me, and I'll be more than happy to discuss it in more detail. Now, the other thing that we have done recently to increase our simulation capability when it comes to installed antennas is we acquired a company in 2015 called Delcross, and from that acquisition we ended up getting two types of solvers, solution tools. One would be the Savant tool, and the other one is the Emit tool. Both of these tools are what enabled us to start placing very small antennas on very large platforms. Now, SBR, in contrast to our traditional finite element solver and our integral equation solver, is what we call a shooting and bouncing ray technology solver. In other words, it is an asymptotic technique. It is complementary to full wave solvers like HFSS, but it is an asymptotic technique, so it is not a full wave solver. It extends the physical optics, the PO that we're all familiar with in terms of ray tracers. It extends that capability with geometrical optics, which is another method to do electromagnetics, to make a very successful and highly accurate ray tracer. However, our tool is called SBR Plus, and the plus really stands for the fact that not only are we having physical optics and geometrical optic ray tracing, we also enhance the accuracy of this particular tool by incorporating physical theory of diffraction, uniform theory of diffraction, and creeping wave solutions. And that, of course, is all there to enhance the accuracy of our SBR tool. And of course, the way this works is that the GTD, UTD, our SBR solver paints currents on a platform body. In other words, the antenna creates electromagnetic fields. Those fields then create current on the bodies, and then the current of those bodies is taken and integrated to give us the electric field at any point in space. What's important to note here is that it doesn't matter whether we use the finite element HFSS solver or the IE HFSS solver in combination with SBR HFSS solver. They all work together seamlessly, right? And they're all engaged together to give our customers the most accurate answer possible. So as we can see here, this is sort of how our SBR technology works. We have an incident ray, and then we can see how those rays bounce off of different structures. and how those different structures then contribute to the electric field everywhere in space. Oftentimes when we deal with very large structures that have very small antennas placed on them, it is useful for our customers to do some model prep or possibly some defeaturing. And we now also offer a tool called Space Claim that works together with HFSS that allows our users to create quite complex simulations that are based on CAD files that a customer can get from their mechanical department. But what Space Claim does allow us to do is allows us to defeature these very complicated full structures into something that might be more amenable to an electromagnetic simulation, right? But we can also create, if we ever get into doing radar for automotives, or if you ever get into doing automotive radar, you can create these very complex street scenes as you've seen here, where you have multiple objects and light poles and cars and trucks, and we can analyze that as well. So we can use Space Claim to defeature highly complex models of airplanes, take away things that are not necessary in an electromagnetic simulation, and we can also use Space Claim to build up these very complex scenes that we're going to analyze from an electromagnetic perspective to help us with the radar simulation that we're doing. Now, of course, ANSYS also has a reliability workflow, so we can use our ANSYS tools to do electrical reliability in the terms of signal integrity and power integrity. We can do electronics cooling. So oftentimes if we have very high power antennas, there will be thermal concerns. Those thermal concerns can be investigated and addressed directly within the ANSYS HFSS tool so that we can see how hot things get and what we need to do to cool them down, right? But then we can also do mechanical and structural reliability, possibly vibration analysis. We could see if a component gets really warm, how it deforms, and then how that deformation of your antenna affects the far field as well as the near field field performance, and of course the return loss and insertion loss performance, the S parameters as well. So not only do we allow our customers to design small antennas with HFSS, we can mount them on large structures, and we can also help our customers determine the thermal integrity or the mechanical integrity or the electrical reliability of their product. So that's a brief overview of the high frequency tool with special emphasis on the SBR tool, because that is the tool that allows us to go to next level when it comes to electromagnetic simulation, which is installed antennas and array modeling. So when we do an installed antenna, I think we're all aware that doing a simple antenna is quite straightforward in a tool such as HFSS. We have antenna synthesis built into HFSS. We have an antenna synthesis toolkit. We also have antenna optimization built into the tool. And we would use our finite element HFSS solver to do this type of antenna modeling when the overall structure is on the order of 10 lambda or less, right? So we're not talking about physical size, we're talking about electrical size, but certainly if your electrical size is less than 10 lambda cubed, then you could use a tool like HFSS finite element. Now, if your structure becomes a little bit larger, so let's say on the order of 100 wavelengths cubed, then what we could use is the IE solver, right? Now, The question, of course, is it more appropriate to use the IE solver or the FEM solver? Well, the answer there really is that it depends on the size, right? If you do get to a quite large model, like 100 lambda, it's probably in your best interest to use the IE solver, provided you have a lot of metal surfaces. So if you were on a car, on an airplane that was 100 lambda in size, you could easily use the IE solver to do that. However, when we're talking about antennas that are installed on a platform, what we're really talking about is thousands of wavelengths, possibly tens of thousands and more. And this is when we have to use this last tool that we talked about a minute ago, the SBR solver. It is the SBR solver that allows us to make the jump from simply modeling an antenna with HFSS to modeling an entire aircraft carrier that has multiple antennas on it and determining what the performance of each of those antennas is going to be. Now, of course, when we have multiple antennas on a platform, whether it's our cell phone that usually has 8, or a car that, according to the latest report, could have anywhere up to 30 antennas, there will always be some co-site interference. Different antennas like to interfere with each other, and thereby we now have a tool called Emit, which is specifically created to allow engineers to investigate the interaction between antennas, not just from an S parameter perspective, but from a signaling perspective, from a perspective where we can incorporate the things like the electronic circuitry at the front end or at the back end, and even some of the modulation schemes to see how much interference we're going to have. But for installed antennas, we have a fairly robust workflow, and it always starts with the HFSS antenna design. And that antenna design is done in what we would call our traditional HFSS solver. Now, we can then incorporate our antennas into what we call a big scene or a large platform as a linked source. And what a linked source is a source that is originally calculated in HFSS. In other words, we simulate the antenna in HFSS only. There is no platform. And once we have that model finished, that will become our source for integrating the antenna onto a platform. And then we can integrate the antenna onto that platform. And there will be two-way interaction between the antenna model that's done in HFSS and the platform, so that we can get the proper antenna gain, the coupling between antennas. We can model MIMO, all of these things, right? So basically what we do is we start with designing an antenna on its own, like we always have in HFSS, and then we can link it to a large platform. It could be thousands of wavelengths long, and in that simulation, we will combine the FEM results with the large model, and those FEM results will become a source, and there will then be two-way interaction between that source antenna and our large platform. And the numerical process that we're using is our SBR asymptotic solver. So we are hybridizing finite element solvers with SBR solvers to do this. So here's an example of what I just mentioned. Here we can see a box that's colored sort of in blue and orange and green, and this would be our HFSS simulation, right? This is I believe this is an antenna, a blade antenna, and what we're simulating in HFSS, the finite element tool, is just the blade antenna and that box that we see. Once that simulation is finished, it becomes a source in the SBR plus simulation, which is this entire jet aircraft. And what we're doing is we are spacing the antennas on the top of this aircraft. And remember, these are HFSS FEM simulations that are becoming the source on this larger aircraft. So we're looking at about 1 gigahertz, and what we can now do is we can look at antenna coupling versus spacing, right? And these are very, very fast simulations. Obviously, the HFSS simulation could take a few minutes, but once it is done and we have our solution to this blade antenna, we can import it into our SBR simulation type, and then we can just simply place it where we would like it to be, and we can then look at all of the types of information an engineer needs, whether it's coupling, whether it's far field patterns, etc. And we can get these simulations really quickly. In under 3 minutes, I will know exactly what my far field's going to be, what my coupling is going to be, etc., for this particular blade antenna on this particular jet aircraft. And these are all full size, right? So in reality, this blade antenna is tiny compared to this jet, but it doesn't matter. We can just combine HFSS with the SBR functionality and get the results that we want. So here's another example of a 15 gigahertz reflector that's mounted in a radome. So in the center picture, we can see that circular disc and that dish antenna, and you can see that it is surrounded by a radome. And we do radome modeling. And again, we've originally modeled the horn and the feed for this horn with HFSS finite element solver, and then we used the SBR tool for the radome, helicopter, and reflector. And that, of course, does include feed horn blockage. And the types of results that you can obtain are shown, well, really on the left. You can see the far field pattern. You can see the modulation that the rotor blades provide to the far field pattern. And you can steer this antenna in any direction that you'd like and see how it's affected by the geometry of the helicopter or any other type of objects that are in proximity. So we can easily simulate real world scenarios when we combine together HFSS and SBR. Now, not only do we do the far field patterns, but we can also do things like gain and self-coupling. So let's say we have multiple antennas on a particular aircraft, and then we can use the simulation to determine what the values are for coupling. In other words, are we going to get some destructive interference when we place our antenna here, or are we going to be okay? Obviously, when we do this type of simulation, we can have mill and arrow standards of communications that we can employ as well. So we're not just looking at fields when we do these types of simulations. We can also look at data transfer, how much data is leaking into our receiver that shouldn't be. Pretty much anything that you could test for. Once we have a simulation situation that uses SBR and HFSS together, pretty much anything that you can test, we can simulate. So before you go off and put your antenna, your prototype antenna on a very expensive platform, you go through all the process, you could develop a virtual prototype that has all the functionality from an electromagnetic perspective of the actual device, and we can see how that device is going to work from an electromagnetic perspective. One of the other things that we like to do with tools like HFSS, we can do characteristic mode analysis, right? Characteristic mode analysis is the analog to an eigen-mode analysis. Characteristic mode analysis uses the IE solver, whereas an eigen-mode solver uses the FEM solver. The the objective of characteristic mode analysis is exactly that. We want to figure out at what frequency these types of platforms, in this case it's a Humvee, resonate at, so that we make sure that we don't have any antennas or communication systems that are impacted by the self-resonance of vehicles, right? So one of the key reasons why we like to use the eigensolver for this is because the eigensolver is ideal for open systems, in other words, things exposed to the air, whereas if we wanted to do an eigensolver using FEM, we would want to do that with a closed system. But in the end, characteristic mode analysis does help us find the optimal antenna placement, right? Because it helps us understand what the natural resonances are of our system. So now we can do a CMA on a single vehicle, and we can then place antennas at different places, or we can also determine, before we place any antennas, we can determine what kind of mode, what kind of antenna pattern we would get from the resonating mode, or from the resonating characteristic of our vehicle. So even though there is no antenna on this car, because it has a resonance, a self-resonance, it's going to radiate, and we can use our tools to figure out what the radiation pattern is going to be by this particular vehicle. And then, of course, we can take that information, or that same model, and we can integrate whip antennas, or a bent whip antenna, or a short vertical antenna. And we can see a couple of things. We can look at how the body of the vehicle impacts our return loss with and without match. We can look at how the vehicle interacts with a bent whip antenna to produce a particular antenna pattern, how it interacts with a short vertical for a particular antenna pattern. In other words, what we're looking at here is not the performance of just the antenna, and not just the radiation of the self resonance of the vehicle, but we are looking at both of them together, because that's the magic of electromagnetics. Everything impacts everything else. So if we really want to truly understand how well our transmit receive antennas are working on a vehicle, we need to incorporate them together. As we can clearly see here, different antennas will have different performances on this vehicle. And again, we can create a virtual duplicate of what we would build in reality, and create and determine how well our system works, system being vehicle and antenna. Now, oftentimes, people do use our tools to model not just single antennas, not just the single whip or fin or blade antenna, but they want to do an array. So we obviously have an array methodology in HFSS, and it's quite straightforward. We start off with a single antenna element, as shown here. This is just a simple dipole antenna. And then once we have that antenna performing the way we want, in other words, once I've tuned it using HFSS, I can take my single element and I can put it into an element array panel, maybe a small one first, an 8-element panel. I can make sure that everything works the way I expect it to in terms of feed network or power or phasing. And once I've got that done, I can create a 128 element phase array. Now, these are all done in HFSS, and you can see these are all 3-dimensional models. So we can now do the finite array analysis, and when we have a 128 phase array, we can solve that in HFSS. However, we within HFSS have tools that allow us to be quite efficient at solving these arrays. Doing a 128 element phased array using brute force is possible in HFSS, but we do have some built-in tools that allow us to solve this 128 element phased array and take into account edge effects and mutual coupling effects without having to brute force this this simulation. And then of course, once we have a solution to the array, we can simply take that solution to the array and we can integrate it with a radome, or we can place the array on a superstructure, whether it's in this case as shown a cell phone communication tower or the side of a battle cruiser. We can then take the HFSS array model, make it a source, and then we can use the SBR solver to help us figure out how this array will work in the real world when it's deployed. So I've mentioned that we have some very clever tools to help us with our array simulation, and that is what we call our finite array domain decomposition capability. And basically what it is an effective, highly accurate, and very fast method to solve the explicit array that we see on the bottom, but in less time. And in order to do that, what we have to do is we have to create what's called a unit cell, right? A unit cell is just the repetitive element of your array. And we analyze it in HFSS. And once we have the unit cell analyzed and it works everything the way it wants to, we could just use the built-in infinite array calculation capability that's in HFSS. However, doing the infinite array approximation, which it is an approximation, will ignore edge effects. You can only do uniform magnitude excitations, and you can only do single scans at per solve. So it's somewhat limited, and that's why we've come up with a few years ago the idea to have a finite array where we can now use our unit cell in a sophisticated manner, and then we can create an array built up out of our unit cells. And when we use the finite array DDM capability, we can analyze the entire array, and we will take into account edge effects, and we will take into account mutual coupling terms. We can do arbitrary excitations, and in the end, we're going to get the same results as if I explicitly modeled this. The only difference will be simulation time. Right? So we can do arrays both explicitly or using our finite array methodology. And it's really just a question of, if you want your answers as fast as possible, then I would encourage you to use the finite array decomposition, the finite array DDM method rather than the explicit method. But you can do both. One is just a lot faster than the other. Now, once we've done a phased array antenna, some of the things we can look at, right, is how does the beam steer? So that would be, what does the beam look like? What are the side lobes? What are the back lobes? Some of the other things that we can do is we can visualize the coupling matrix. So what we're looking at here is 128 by 128 antennas, right? So 128 across, 128 down. So that's going to be our 128 array, element array. And the graphic really shows us the coupling between different array elements. Obviously, the central diagonal should be the highest coupling because that's where the antennas are closest, but then we can also quite quickly see how much coupling there is to all of the other antennas as well. And then, of course, once we have our electromagnetic solution for an array, we can take it through the same process that we talked about earlier. We can take those HFSS models and we can make them be sources on a larger structure. In this case, it's a cell phone tower. And we can then choose whether we want to use the IE solver, depending on the size of the cell tower. If it's a reasonable size, we could use the IE solver and do everything in terms of a full wave electromagnetic simulation. But if our superstructure or platform becomes too large, then we can do our SBR solver in combination with HFSS. What is important to note here is that we do allow for hybridization of numerical methods to allow our engineering customers to solve the biggest models possible, right? We have pretty much pioneered the use of hybridized numerical techniques in electromagnetics, and all of our solvers, whether you're a finite element solver, the IE solver, or the shooting bouncing ray solver, the SBR solver, they all lend themselves towards this hybridization. So there should be no reason at all for somebody to not be able to do a full analysis of a full antenna system on a full platform. And that's it for these first two parts. As I've mentioned before, if you have any questions, this would be the perfect time to ask them. And if you'd like to see one or more of the other sections, I'd be more than happy to work with KETIV and present you additional sections out of what we can do with our tools in the realm of antenna design, antenna platform design, and radar design. That's all I have for today. So if you guys have some questions, I'd be very happy to answer them. Thank you.
Thank you. Thank you so much, Markus. This was really good. I got to learn so much about, HFSS capabilities for antenna design. So thank you, Markus. Thank you so much for this session. This was really useful, and hopefully we'll have you soon again for the other features that ANSYS has to offer.
Thank you very much for paying attention, for everyone for attending. Have a great day.
You as well, Markus. Thank you.
Thank you.